Today we're going to learn about a new force. In our class so far we've talked about normal force, we've talked about the force of gravity, we've talked about tension, we've talked about applied force, and we've talked about the force of friction. I'm going to teach you a new force today, and I'm going to use this equipment to help me show you what the new force is all about. So I've got a spring scale right here that reads the weight of whatever's hanging on it. I've got a bucket on the bottom that I've arranged the scale so that it reads 0 right now, even though of course this doesn't have 0. I've just zeroed it out, kind of like you did in chemistry last year with the tare button. And I've got an overflow can here where I can, right now it's filled with water, and if I add some more water to that, then the water overflows out the side and goes right into the bucket. And hopefully you can see that coming out, and if you can't see the water coming out, you can probably hear it, or you can see the weight increasing on the spring scale as it fills up with water. The purpose of this is that as I put something into this, for every volume that I put in here, each little drop, if you will, of substance, whatever it is, some water overflows out the side and into the can, so we can see how much water, or rather the weight of the water that is in the can. So I'm going to dump this out, so we're starting back at square one. And then I'm going to add to that this weight, which as of right now you can see that this is 10 newtons of weight, which translates, as you could probably figure out, to 1 kilogram. 1 kilogram times about 9.8 meters per second squared gives us about 10 newtons. I want you to watch what happens as I put this in the water. I can't see it, of course, but I know that you can. And as I put this in there, you should notice some of the water is coming out of the vessel, and it's going into the can there. And I hope that what you're seeing is the force in the bucket, the weight of the water, is increasing as the weight on the one that I'm holding is decreasing. In other words, there's an upward force from that water pushing on the weight that I'm holding. We call it a buoyant force. The buoyant force is pushing up on the weight in the water. And I want you to notice that this went down as much as this went up. In other words, the weight of the water in the can is equal to the force of buoyancy upward on the mass that's in the water. Okay, let me get this out of the way, and then we'll talk more about it. This idea, this force, it was first discovered by Archimedes, so it's called the Archimedes principle. If you're interested in a good story, maybe I'll share that in class sometime, or you can look it up, but Archimedes has an interesting story about how he discovered this. The Archimedes principle you need to know, so I'll recite it to you, and of course, since you're taking notes, you're going to write it down in your notes. So here is the Archimedes principle. An immersed object is buoyed up by a force equal to the weight of the fluid it displaces. It's kind of hard to understand. So let's talk some more about that. An immersed object is buoyed up by a force equal to the weight of the fluid it displaces. Now, to break that down in terms of the demonstration you just saw, this is just stating what the demonstration showed you, right? The immersed object, that's the mass that I was holding on to that went down into the water. That object is buoyed up, so that's where our force of buoyancy comes from, is buoyed up by a force, so it's upward force, and that force is equal to the weight of the fluid it displaced. That was the water that overflowed into the bucket. So that those two forces, the upward force, the buoyant force, is equal to the force of gravity, or the weight, of the fluid it displaces. Now, usually from statements like this, we can get an equation, which is what we want to talk about here too. So, from that statement, we can get this equation. The force of buoyancy, which we'll just call force of buoyancy, is equal to the weight of the fluid displaced. Now I'm going to write it like this, and I'm going to ask you to prove it to me later that it's equal to the weight. So this is the Greek letter rho, which stands for density, times G times V. This is a capital V, so we're not talking about velocity, we're talking about volume. And you might want to know what each of those things stands for. So again, I would recommend you write this in your notes. This, of course, is force of buoyancy, which is measured as all forces are in newtons. This is the Greek letter rho, which stands for density. And this density will be measured in kilograms per meter cubed. G, you know, is the acceleration due to gravity. So here on Earth, that's 9.8 meters per second squared. V is the volume. This is the volume in meters cubed. And it's the volume of the fluid displaced. That's really important that you know it's the volume of the fluid displaced. The volume that is pushed out of the way. And it's the volume of the fluid that is pushed out of the way. So in this case, water was pushed out of the way. That was our fluid. And we're talking about the weight of that fluid, which comes right back to Archimedes' principle. So one of the things I'm going to ask you to do, and I'll just say it right now, is I want you to prove to me, in your notes there, that the force of buoyancy is equal to the weight. Show me that this is the same thing as weight, which is another word for saying force of gravity. So you can do that in your notes, and I'll ask you that on the Google form as well. Now, how do you use this stuff? I'm sure you're wanting to know, so let me give you an example problem. We'll kind of work through at least the beginning parts of it. Let's say that we have a balloon which is filled with helium and it's attached to a table by a string. So there's my table, and here's my helium.
Sanju Cho, please come to the main office. Sanju Cho, please come to the main office.
Let's add this string nice and taut so it's got tension on it. And this is, now it's taped to the table, and there's a buoyant force on the balloon. That's why the balloon wants to float or rise up, and that's why it's kind of being held back by this tension. We got tension down and the force of buoyancy up. So the question I have for you is, what is the tension in the string? And let me give you some things that we know about this balloon that will help us solve this. First of all, we know the...
Pedro, please come to the main office. Pedro, please come to the main office.
We know the mass of the balloon. I'm just going to make this up. The mass of the balloon is 0.003 kilograms. We know the volume of the balloon. Again, I'm going to just make this up for the purposes of doing the problem. It's 0.005 meters cubed. We know the density of air. And that value is 1.29 kilograms per meter cubed. And lastly, we know the density of helium. And that is 0.179 kilograms per meter cubed. So, as with any force problem, and you know this is true, the first thing you need to do is draw a free body diagram. So, I think you should pause the video right now and take a second to draw a free body diagram, just to test yourself, and then see if your answer matches mine. So when I draw my free body diagram, I'm going to free the balloon from the rest of the picture there, and there's my balloon. I've got a few forces acting on it. I've got force of gravity down. I've also got a force of tension down. And then I've got a force, it's not buoyant, I'm sorry, it's not normal. This is the buoyant force that's acting up on this. Okay, next step. Hopefully, again, I think you should stop the video here and see if you can figure out the next step. Then start it up again to see if you're correct. So our next step, as in any force problem, is to write the sum of forces equation. In this case, there is no x force. There's no x movement at all, so we don't even care about the x forces. We're just looking at the y forces. That's all that exists. And then we have to ask ourselves, okay, what is the acceleration here? And it seems to me that this balloon is at rest. It's taped down. So the acceleration then is 0. So I can say the sum of the forces equals 0 newtons. Well, then how many forces are there? Well, we got a...
Pedro, please call 2600. Pedro, please call 2600.
If only Pedro could come help us with this problem, it might be a little easier. So I've got force of buoyancy up. I've got two forces that are down, so I'll do subtract the force of tension, subtract the force of gravity, and I get still 0 newtons. So I just expanded this side. This is the sum of forces. What are the forces we're adding? There they are. 1 up, that's positive. 2 downs, those are negative. And at this point, then, you're going to write in the stuff that you know. You'll fill in the equation. So the force of buoyancy is rho GV. There is no equation for force of tension. Force of gravity, you know, is m times g. And that equals 0 newtons. Now, I'm not going to run through the whole thing because I know that you can plug in numbers over here. You, of course, will put the mass of the balloon here. Don't forget sometimes we have this thing filled with helium, and helium has mass to it. So we got the mass of the balloon and the helium times 9.8. Force of tension, there is no equation for, but I want to focus on this, of course, because this is our new equation and our new force. So the question we have to think about here, and this is where it gets difficult, it's easy to make a mistake here, is what do you plug in for the density, what do you plug in for the volume? G is easy, that's 9.8 here on Earth. You have two densities to choose from, density of air and density of helium. Well, in your notes, as I wrote on the board a few minutes ago, this volume and this density are always about the fluid displaced. So what fluid is pushed out of the way? Is it air that's pushed out of the way by the balloon? Or is it helium that is pushed out of the way by the balloon? The helium is inside, and the helium displaces the air. It pushes the air out of the way. So this density that you have to plug in is the fluid displaced, the fluid moved. That's the density of air in this case. So I would plug in 1.29 kilograms per meter cubed times the 9.8 meters per second squared times the volume, and the volume is given here for us 0.005. That's the volume. In this case, the volume of the balloon matches the volume of the fluid displaced, but that's not always true. So this V is always the volume of the fluid displaced, not necessarily the object. That'll be helpful in tomorrow's problems. And then you would just go from there. Again, I'm not going to finish it all. I'm going to let you finish it and answer that on the Google form.